Okay, welcome to the second week of chemistry. And as usual, before we start class, we're going to have a bevy of advertisements to go through for different organizations. So let me zoom in a little bit on these. Just zoom out once. All right, so anyway, the first one that I have is the American Student Dental Association. So these will be in the notes. I'm not going to go through all the details, but they have their first general meeting. I guess it's tonight, so I didn't get this until recently, so you don't have much notice. But that would be tonight if you want to pursue a career in dentistry. And there are more pre-medical societies at UH than I ever knew existed. So one other one is Delta Omega Chi. This is for all aspiring health professionals, apparently. And they also have a meeting tonight, right after class. And then the one that you have a little bit more notice on, at least a day's notice, is Alpha Epsilon Delta. So we're going through the Greek alphabet today with all these honor societies, and they have their own pre-medical honor society. So there are a lot of these, and I don't honestly know the difference between all of them, but they're all good organizations, and if you have aspirations in any of these fields, it's good to check them out and become a member of that. But what we have to talk about today is getting into Chapter 2. So we did finish the first chapter of the book, which was kind of the real basic elements of chemistry with respect to mass laws. And we finished up last time talking about the structure of the atom to some extent. So we talked about subatomic particles, the nucleus, electrons. Now what we're going to get into in this chapter, and what really dominates the rest of chemistry in some respect, is what about the electrons in the atom? So we're kind of more or less done talking about the nucleus. We saw that the nucleus has protons and neutrons. It's really dense. It has almost all of the mass contained in it. But it's actually the electrons that are the more important thing to think about in most chemistry contexts. And we kind of closed our model of the atom last time with kind of just the idea that there's this electron cloud. It's pretty diffuse. There's a lot of empty space, but what really is going on with the electrons, and that's what we're going to get into starting in this chapter. So to be able to then start introducing that, we have to talk a little bit about electromagnetic radiation. Now this is going to seem like a purely physics topic, and you might be wondering why we even include it at all in a chemistry course, but the reality is people will learn things about electrons by studying the interactions of electromagnetic radiation with chemical matter. So it's really that interaction between the two that gave us a lot of the key ideas about electrons and how they behave in atoms and molecules. So we need to know a little bit about electromagnetic radiation and light in particular, which is going to be a key concept, a key component of all of this. So first let's give sort of the physics definition of electromagnetic wave, or radiation as it's often called. So you'll see the term wave and radiation used sort of interchangeably. And so what we have here is it's a form of energy that's propagated by electric and magnetic fields. All right, so again, this is a very physics definition that's not going to be terribly important. We want to know at least a little bit more what they are. And these electric field, magnetic field, they oscillate, they go together, so you can't have one without the other, but they oscillate in intensity as they travel. So this is a picture that I stole from somewhere online about what these look like. And so what it's representing here in blue is the electric field that oscillates as time, and then red is the magnetic field, labeled B in this case, that also oscillates in a perpendicular direction from a spatial standpoint. So as I said, you can't really have one without the other. The electromagnetic parts always go together. They always have the same attributes as one another, but they are both really there. But this sort of three-dimensional picture is not going to be one that we're going to really use a lot. Typically, we'll just decompose the wave into a two-dimensional picture that just shows one of the oscillating waves with the assumption that the two are actually oscillating together. It's a much simpler picture, much easier to draw and look at. So these sorts of diagrams, and again, we'll primarily use the simpler ones later on, they can be interpreted sort of in two ways. So one is kind of explicitly shown here is using distance coordinates, x, y, and z. So if you have one of these waves and you can imagine that you just froze it in time, just took a picture of it, or or whatever the case is, you would see these sort of oscillations in space. So as you go from left to right in whatever direction, if x direction is as shown here, you would see that the intensity is lower and higher and oscillates between the two as you go along in that direction. So that's kind of one way to think about these waves. The other way is to think about this horizontal axis as time. And so imagine that you're standing still at one place and this wave is traveling in front of you. What you would see is an up and down oscillation. So the intensity of the electromagnetic field would go up and down in time as you sit there and watch it. And it would go, and then that would sort of give you this picture here where you have, again, intensity that oscillates between high and low as it goes along. So that's kind of the picture. Now, examples of electromagnetic radiation that you're all likely familiar with. So visible light, the light that we see, is one category. And we'll talk about what distinguishes these from each other here in a minute. X-rays, which have obviously very important uses in medicine and other technologies. And then when you listen, or if anybody listens to the radio anymore, I still do because I'm old, but if you listen to the radio, that's radio waves as a form of electromagnetic radiation, and then the microwaves that you would use to reheat food also fall in this category of electromagnetic radiation. So a lot of these things that you've heard of are all different forms of electromagnetic radiation. So let's talk about then the properties of a wave, which is going to then, as we'll see, dictate the differences between all these different forms that we have. So we're going to do a little bit of color coding here. So one of the key properties is called frequency, which is going to have a Greek letter abbreviation nu. So it's good that we had all those advertisements because we're going to start using a lot of Greek letters ourselves today. So we got a little primer. So nu is like a V that has a strong wind blowing from left to right, so you kind of like a tilted V. I didn't draw it particularly obvious here, but it looks maybe something like this, a little bit more exaggerated. So kind of like a sideways V, like you're blowing wind into it. I'm going to try to get you to learn some of these Greek letters because they show up a lot in chemistry and other areas of science. Anyway, so frequency can be thought of as the number of cycles or number of oscillations per second. Now the unit for frequency can either be just inverse seconds, it's just how many counts per second, or it's been named since then after famous scientist Hertz, so it'll be abbreviated Hz for Hertz. Now if you're going to sort of look at this picture of a electromagnetic wave and say, well, what does frequency mean? You would have to then assume in this situation that the horizontal axis is going to be time in this case. So let's say that this horizontal distance represents 1 second, again being arbitrary here but just for illustrative purposes. So if this is 1 second, we can count how many cycles does this wave go through in 1 second. Now a better way to think about this one is, again, imagine the situation where you're standing still watching a wave go in front of your face. Count how many times the intensity goes up and down in 1 second. So if this is 1 second, we can count the number of cycles. So it's going to be one complete cycle. So crest to crest if we're starting at the top here. So that's 1, 2, follow the highlighter, hopefully you can see it. Yes, 3, and 4. So this wave would have 4 cycles per second if this is defined as 1 second as I've shown it here. And so that would mean the frequency of this arbitrary wave on this scale would be defined as 4 per second, or equivalently written as 4 hertz. All right, so that's what we mean by frequency. It's the number of oscillations per second. And now the other key parameter of a wave is wavelength. And this is the distance between equivalent points on the wave. So distance between equivalent points is wavelength. And so for this sort of picture, you have to then take this picture of the wave as being stretched out in the x direction, or a snapshot in time, and you're looking at horizontal distance across the wave in this case. So lambda would be the distance between equivalent points, and it can be defined in a lot of different ways. So if we start at one crest in our wave, lambda would be the distance until you get to the next peak or crest in, crest in the wave or peak. So that's lambda. That's one lambda there. Or it would be the same distance if we took the distance between two troughs, between two minima. That would also be lambda. So two equivalent points in the wave, the distance between them, as you can tell if I drew this relatively accurately, those distances are equal to each other. It doesn't matter what your reference points are. And then, or we could do, for example, the point where this wave crosses the 0 point. And that would also be considered lambda as well. So as long as you're just traveling between two equivalent points on the wave, the distance between those will be lambda, and you'll get the same lambda no matter how you measure it. So that's the length of each cycle of the wave as you sort of freeze it in the horizontal direction. And then the last one, which isn't so terribly important for us, as we'll see, but was kind of a big deal when they first started talking about waves, in the classical sense. So this wave picture of electromagnetic radiation is a very classical picture. We're going to learn kind of the more modern picture today, which combines this with other ideas. But in the classical sense, there's also this third parameter that's important called amplitude, which is abbreviated as A. And this is the height of the crest of the wave. And it can kind of be synonymously thought of as the intensity of the wave. So, real simple picture, if you have a really dim light, that would have low amplitude. If you have a laser that's powerful enough to shoot your eye out, that would be really high amplitude, really large amplitude. So amplitude is just related to how intense the electromagnetic radiation is. So it would be on the graph then, it would be this distance here from the midpoint of the wave, not from bottom to top, but from the midpoint to the top is the precise definition of amplitude. And like I said, that one, you could also define it as midpoint to bottom. That's the same distance, but it's not top to bottom, it's midpoint to either the top or the bottom. So those are two ways of diagramming amplitude on this graph. Again, from a classical standpoint, that was important because that was believed to be what determined the intensity of the electromagnetic radiation. We'll see that that's not quite right, and regardless of whether it's right or wrong, it's not something we really have to think about when we're talking about the properties of waves in the context of chemistry. All right, so let's move on then and talk about then how we compare different waves. So this is just expanding on what we learned in the last one and just comparing two different waves, A in blue as I've had it, B in red. So if we compare the wavelengths and the frequencies, we have to then, so lambda A is going to be this distance here, let's say. So A is the blue wave, and we're going again from two equivalent points on the wave, which would be, let's say, the crest to crest. And if we count then I have some horizontal markings here so you can count. So this is our wavelength or lambda for the first wave A. And in whatever arbitrary units we have on this graph here, we count. We go 1, 2, 3, 4, 5, 6, 7, 8. So 8 divisions, 8 of those horizontal markings get us from one point to the other. So the wavelength on this scale would be 8, whatever unit it is, not specified. If we go to wave B, which is in red, and we measure its wavelength, again we go from two equivalent points on the second wave, which would be those two, for example. Doesn't have to be those two, but that's one way of doing it. So this distance here for wave B is going to be 4 on whatever scale this is. So we count again the number of divisions between each equivalent point. 1, 2, 3, 4 to get us back to where we started. So so the relative wavelengths of these two then would be, if we're just doing it in a relative sense, the wavelength of A is 2 times the wavelength of B. All right? So that's one relationship between these two. Now let's look at frequency. So again, for frequency, we're going to assume that our horizontal axis is now a unit of time. And so if we go for, let's say, this unit of time here from this position. Now if we're going to compare frequencies, we have to compare the same unit of time, or at least normalized unit of time. So let's say we're taking this section here, assuming it's some unit of time, and in that unit of time, wave A goes through how many cycles? Let's count it. Wave A starts here, we go 1, and we go 2 to get to the end of that segment that I've drawn out here. Again, you could draw any arbitrary segment as long as you count the cycles appropriately. This gives us nice whole numbers, so that's why I picked it. So in that span of time, A traverses 2 cycles, If we go to wave B over the same period of time, so now we're looking at the red wave here over the same period of time, we compare the two, and we're going to go 1, 2, 3, 4. So wave A would go 4 cycles in that same unit of time. So again, with these arbitrary units that I've given here, or unitless I guess is the more accurate way to put it, the frequency of A is going to be 1/2 times the frequency of B, because wave B goes through twice as many cycles as A in the same unit of time. So what you might notice that we're going to come back to here in a second is that there's sort of this inverse relationship. The wavelength of A is 2 times the wavelength of B, but the frequency of A is 1/2 the frequency of B. So there's this inverse relationship between frequency and wavelength. We're going to come back to the importance of that here in just a second, but first let's do a quick comparison of amplitude, which I said is not terribly important, but just to drive the point home so we can leave this behind. So for wave A, if we want to measure the amplitude, again, in this case we need a vertical scale, which I provided. So amplitude goes from the center point, so this line here is the center point of both of our waves, and we go for A to that crest there, so that's 2 units on our scale as I've drawn it out, or alternatively it's 10 of these small units if you want to count the small ones, but we're not building watches here, so we can just say that that's 2 of the big divisions is amplitude for A. And if we do for the red wave B, so in the previous example they had the same amplitude if you noticed. In this case they're different, and for wave B we would go, for example, from here to here. That's only 1 vertical scale, 1 on our vertical scale. So I'll call that a 1. And so the relative ones again would be A is twice the amplitude of B. And you would say then that A is brighter or more intense, whatever kind of radiation it is. So that's the classical picture. Now we're not going to actually see any equations that involve intensity or amplitude. I've kind of told you that it's not terribly important for us in chemistry. But what we are going to start developing now is relationships between the other 2 parameters, which is wavelength and frequency. And I kind of, gave the hint, or let the cat out of the bag a little bit, which is that there is this very obvious relationship between the two. We saw in the example that I gave you 2 slides ago that there's an inverse relationship. So if the wavelength of one of the waves is twice the wavelength of the other, the frequency would only be half. And so then we can write that mathematically as lambda is proportional to 1 over the frequency. So whenever things are inversely related, that's what it means mathematically. This little sign here means proportional to, it doesn't mean equal to, it just means that they're related in that way. And then a common trick we're going to play when we derive a lot of equations in this course, this being the first one we'll do, is if you want to turn something that's a proportionality into an equality, into something that, an equation, you just have to add a constant to one side or the other. Okay? So we can add a constant to either side. The one that was conventionally done is to add the constant to the right side of the equation, so we could just write that lambda is equal to a constant c over the frequency nu. So that's sort of really our first equation for a wave. Or you can write it as just the product of the two, lambda times nu, or nu times lambda as I've written it here, is equal to c. Now c has a very specific value, and it's a very special constant for us. It's not just a random numerical constant that's different for every system. It is actually the speed of light. So if you think about dimensional analysis, we're multiplying a distance unit by 1 over time. So that's going to be distance per time, which is speed. So c is the speed of light. And this constant is on your periodic table, so you don't have to memorize it, but you'll use it enough that I suspect you will. And it's 3 times 10 to the 8th meters per second. Now that specifically refers to a vacuum, meaning that that's how fast light travels when there's no other matter present, no air or anything around it. It's slightly different in other situations, but even in air on Earth, it's not that much different than 3 times 10 to the 8th. Air doesn't affect the speed of light that much. But at any rate, this is the standard that we use, 3 times 10 to the 8th meters per second for the speed of light. And so now we have an equation where if we know either the wavelength or the frequency, we can easily find the other of the two, because they are related to each other in this simple way. And again, to show you, just so you know, in case you don't believe me or haven't looked at it yet, here's our periodic table, and it's, even though it's the first constant we've covered, it's the last one listed here. And as you can see, we give you slightly more significant digits than you probably need, but it is 3 times 10 to the 8th, and you don't have to worry about memorizing it because it's there for you. All right, so that's our first equation we learned. Now, the other thing that I'm showing on this slide is when we're categorizing the different types of electromagnetic radiation, and these categories are somewhat arbitrary, but they do depend a little bit on some of the key properties of them that we won't really get into details of. But at any rate, when you categorize different types of electromagnetic radiation, the difference between them is the wavelength or the frequency. So you categorize them in that way. And this is the scale that I'm showing in the order. And you should be familiar with the order that these come in. So this is going from lower to higher wavelength, left to right. And since the two are inversely related, that means it's going from lower to higher frequency, right to left. Okay? So the scales are obviously inverted because the two are inversely related. But we should know the order. So the highest frequency electromagnetic radiation is gamma ray. And then comes X-ray, and then ultraviolet. Then we have this little sliver here that's the visible range. So really, compared to the whole scale of electromagnetic radiation, the light that we can see is a very small piece of that. That's shown here sort of in the middle. So you have basically 3 that are higher frequency or lower wavelength than the visible light we can see. You have 3 that are longer wavelength or lower frequency. So infrared is the first one, and then microwave, and then radio. So try to become familiar with this order. It might come up in some of the questions. The other thing that's helpful to know is that this little piece of the visible range goes from about 400 to 750 nanometers. So nanometers is 10 to the minus 9 meters. That's a pretty small wavelength. The frequency values correspond to that are shown here. All right, so this is the typical Roy G. Biv spectrum, although it's written in the opposite direction here, where red is the longest wavelength or lowest frequency. Then you have orange, yellow, green, blue, violet in that order, where violet is the lowest wavelength or the highest frequency. Okay, so this qualitative picture is helpful to know. If those numbers are a little bit small for you, the wavelength again here is 400 to 750 nanometers. That's kind of the scale for visible radiation. All right, so that's how we kind of categorize electromagnetic radiation, is on the basis of those two parameters, wavelength and frequency. Let's do a couple example problems of that relationship now that we've learned it. So we have, in this case, we have 600 nanometer light, which is orange in color. We want to know what is this frequency. So anytime we're talking about properties of electromagnetic radiation or light, which is the one that we'll see a lot in this course, we should just think of this first simple equation we learned. We're going to learn one other one today that's not too much more complicated, which is just that the frequency times the wavelength equals c, which is the speed of light. Here we're solving for frequency, so we just rearrange the equation and write that frequency nu is equal to c divided by lambda. And we just start plugging things in. But here is where probably the first type of problem, and I'm going to harp on this all the time in this course, so you guys are going to probably hate me for it by the end, but I think it's very important to always write out your units. So if we put these numbers in, you know, a lot of you guys are calculator wizards and really good at math, and you want to just start crunching numbers and be done with it, but you have to think about the units anytime you're doing a problem like this or any problem in chemistry. And so if we put the speed of light in, the standard form for that is 3 times 10 to the 8th meters per second. But if we want our distance unit to divide out, that means our denominator also has to be in meters. Okay, the units on the top and the bottom have to be the same for that to divide out. And unfortunately, or as is commonly the case, our wavelength is given to us in nanometers. That's a very common unit for wavelength because that's the, again, the scale of light that we see is from 400 to 700 or something like that. So we need to convert that into meters, and this is where that review chapter is going to be helpful. So I reproduced this table from the book, if you don't have the book, which gives us all of these metric prefixes that we're going to encounter. Now, we're not going to see all of these, but some of them will be more common than others. And the one that we're going to see a lot in this is nano, which is abbreviated with small letter n, and that means 10 to the minus 9. So 1 nanometer is 10 to the minus 9 meters. Or alternatively, 1 meter is 10 to the 9th nanometers. There's two different ways of thinking about that conversion. But we have to convert our wavelength into meters. So that's going to be the first step in this problem. So our wavelength is 600 nanometers. And I don't particularly like dealing with negative exponents if I don't have to. So the way that I'll typically write this conversion is 1 meter is 10 to the 9th nanometers. You could also write it as 10 to the minus 9 on top. Those are mathematically equivalent. But the point is we want nanometers to cancel out and convert into meters, so we're going to do it this way. And so when we multiply those across, we get 6.000 times 10 to the minus 7 meters. So it's always helpful to check yourself when you're doing numerical problems also. So if you're doing a problem that involves electromagnetic radiation, especially if it's pretty clear that we're talking about visible or ultraviolet or near infrared, kind of that narrow region that is close to what we see, you should get in your wavelength on the order of 10 to the minus 6, 10 to the minus 7, something like that. If you're way off from that, you might want to check your math. It might mean you've messed something up. All right. And regardless of the situation, it is important to know those prefixes in that table R2, which I've reproduced here for your benefit, but it's in the book. And so there's all these different metric prefixes that basically just are order of magnitude prefixes, so nanometer being 10 to the minus 9, smaller than a meter. So now that we've converted into the correct unit, we can put this in and we divide. So when we divide the two, we get, we're being careful with significant figures, which is not always that important in this course. We get 5.0000 times 10 to the 14th. Remember, the conventional way of writing the frequency unit is in hertz, or you can write it as inverse seconds. I didn't specify a unit here, but if we want to convert this into a more conventional, we could look at tera being 10 to the 12th is a common one that's used. So this would be 500, maybe. It's not fun to write. Here we go. So another way to write this would be 500 terahertz, because again, 10 to the 14th is a large number, so we often use prefixes to make it a more manageable number. So terahertz, megahertz, those are common ones for frequency. And then you've probably, whether you realize it or not, you've probably seen the unit megahertz before. That'd be a few factors smaller than this. So if you have your radio dial, if any of you still listen to radio like I do, those numbers on the radio, which are, for the AM, are usually like in the 700 to 1000 range, and the FM you have about 89 to 109 or something like that, or 107. Those are megahertz frequencies. So those numbers on the radio dial tell you what frequency of radio waves you'll be picking up when you set the dial to that number, and those numbers are in units of megahertz, which is another related frequency to that. So this would be, visible radiation is quite a bit higher frequency than the radio waves, but you've probably encountered that in your everyday life before. All right, so that's just an example problem relating wavelength and frequency. Obviously, we could go in the other direction. If we gave you frequency, you'd be able to solve for wavelength, and it's really just one simple relationship you have to worry about for that. Now, what we want to get into now is sort of some of the ideas, some of the challenges or confusion that came about, if you will, by studying the interaction of light with matter. So there was a period of time in the early 20th century, not too long ago, on this time scale of human existence, where a lot of physicists, even very prominent ones, some of the most famous physicists in the world at that time, kind of came to the conclusion that, pretty much physics is a solved problem. Let's just kind of, wrap things up, close up shop, and move on to the next thing. They kind of thought that, Newtonian physics, that physics that you'll probably learn mostly in the first semester of physics you take here, explained everything, classical physics as it is now called. And they were kind of wrong about that. So some, people came around, started doing some more experiments, and there was some confusion that arose where basically they would do experiments that they couldn't predict the results using classical physics. They knew that something was missing. And one of the first key experiments that kind of made some physicists realize that the story wasn't complete was this idea of blackbody radiation. Now, this is also something that you've seen in your everyday life. If you have an electric stove, or if you work as a blacksmith on, on the weekends, if you heat up metal to a really high temperature, it starts to glow, give off light. Now, in reality, it's always giving off light, but you can't start to see that until the temperature gets to about 500 degrees Celsius or so. So anyway, if you take pieces of metal and heat them up, or many other substances as well, they start glowing. And this is an example here. I think this is like one of those wood burners, or that you use or a soldering iron or something like that. Anyway, this concept you've likely seen before. All right, so if we take a solid, as long as the solid doesn't burn, so that's why metals are the most common one for this to work in, because they don't burn under intense heating. But if a solid is heated to very high temperature, and again, 500 degrees Celsius is about the threshold when you'll start to see visible light anyway. Although it's more obvious and more easy if you take it up to about 1,000 Kelvin, which is more like 700, 800 degrees Celsius. Anyway, if you heat them this high, they emit visible light. All right, so this has been known for a long time in concept, but then there's some physicists that began studying this in more detail. They were basically measuring the amount of energy that came off as a function of wavelength or frequency, and they were using classical physics to predict what should that profile look like. In other words, at each wavelength, how much light should we get? And what classical physics predicted so it says that matter can absorb or emit any quantity of light, or any quantity of energy, I guess is a better way of saying it. So that, in other words, the energy that's given off by a solid when you heat it up is continuous. And there's a lot of in-depth physics and things that goes into this. But essentially what they predicted is that if you have a black-body solid like this, heated up to high temperature, as you go to the ultraviolet, the amount of ultraviolet light is going to basically just scale up to infinity. You're going to give your intensity in the ultraviolet region is going to be like super high. It's going to go off the scale. And that's not actually what happens. In reality, you get sort of a peak wavelength at some value, and then it tails off as you go in either direction. So, in other words, without the details being that important here, classical physics did not predict the quantitative observation that they saw with blackbody radiation. So, this classical physics fails to explain or predict the wavelength intensity relationship. Of blackbody radiation. All right, so again, to reiterate what I just said, you essentially have, when you have blackbody radiation, every wavelength of light is given off simultaneously. It's not just one or two or a select few. It's every wavelength of light, but they're not all going to have the same intensity. You're going to have a little tiny bit of near infrared, a little tiny bit of ultraviolet, and then somewhere in the middle is where your peak, in this case yellow or orange as we're showing here, would be observed. And that depends on temperature. So as you heat the solid up to different temperatures, the wavelength profile shifts. But the point is, classical physics predicted that the ultraviolet, you'd have infinite intensity. It would trend towards infinity in the ultraviolet. In reality, that's not what happened, so there was a problem. So the solution, and again, why, how does this solution actually address the problem is really beyond the scope of this course. But the solution that Max Planck came up with is that the energy that's given off by these solids, or the energy levels that they possess that's resulting in the generation of this light, is what's called quantized. All right, so that's the key word here. And so you can't just have any random quantity of energy, but they're actually quantized into whole number multiples of this constant h times the frequency. All right, so you're going to have at each frequency you're going to have some smallest unit of energy, and you can't just add those all together continuously, they're actually little packets. Now, h nu is a very small quantity, so in reality, electromagnetic radiation more or less looks like it's continuous, but you can't have fractional multiples of h nu for the amount of energy that's given off by electromagnetic radiation. And so when you factored this idea into the mathematical relationships that govern blackbody radiation, now everything fit perfectly. And again, we're not going to give you those mathematical relationships because they're pretty complicated, but really the things you need to understand are, this is the problem. Blackbody radiation was one of those phenomena that people have been studying, and classical physics couldn't explain it, and the solution was to introduce the idea that the electromagnetic radiation that gives off is some multiple of h nu. So in other words, the change in energy for the solid has to be some whole number multiple n times h times the frequency. And h is now named after Max Planck. It's called Planck's constant, and it's a very small number, as you'll see, 6.626 times 10 to the minus 34 joule second. That's Planck's constant. Alright, but this was the first time that someone introduced the idea that you can't just have any continuous value of energy for electromagnetic radiation, but rather you can have 1 times h nu, 2 times h nu, 3 times h nu, n has to be an integer for this to work. Whereas classical physics would have said that any multiple of h nu could be the energy that's given off by a blackbody solid. So you could have 1.3 times h nu, 1.4, 1.7, whatever. It's continuous in classical physics, but this was introduced the idea that this energy is quantized into little packets of energy given by h nu. Now that's kind of a little bit more abstract one, because we don't have clear relationships that we can look at, and it's not a very intuitive one. But the one that I think really helps us understand this idea of quantization of photon energy, or quantization of electromagnetic energy, is what's called the photoelectric effect. So this was another set of experiments that were done that really failed to explain, or really were failed to explain by classical physics, where people realized that, well, the picture that we have now is certainly not complete. So the person that studied this you've probably heard of before, Albert Einstein. So this is one of his many important contributions to physics, and this one has a little bit of chemistry relevance as well. So here's the idea with the photoelectric effect. So if you have light that strikes the surface of a metal, you will eject electrons from the surface. So we'll learn later on how in metals the electrons are not held very tightly by the nucleus, so it's pretty easy to kick them out and completely eject them from the surface. And even just shining light on the surface of a metal results in some electrons being eliminated from the surface. Now here's the problem though, and that's kind of illustrated with this picture here that I'll go through. So the problem is that what we're showing here is, if you have 700 nanometer radiation. So this picture is for potassium, is our metal, one of the metals on the periodic table, one of the many ones. But for potassium, what they would find is if they use 700 nanometer light, which is pretty deep red light, no matter how intense they made that light, they didn't get a single electron coming off the surface. So again, classical physics sort of assumed that light energy was continuous and additive, which would just state that, well, if you just hit it with more light, eventually they're going to come off. But they never saw it. So they could use, you could use the world's most powerful red laser, and if you shine on the surface of potassium, you're not going to get a single electron coming off of there. However, if they go to green light, which is lower wavelength, 550 nanometers, they saw electrons coming off the surface with some velocity. If they went to blue light, they saw electrons coming off with a higher velocity. So in other words, there's some threshold frequency where if you're below that threshold frequency or above that threshold wavelength, nothing happens, and then after that is when you start seeing the effect. So the light, in order for this photoelectric effect to be observed, the light must have a minimum threshold frequency. So if you're below this frequency, no electrons are ejected regardless of how intense the light is. And the solution to this was the idea that light consists of little, I'll put this in quotes because it's not really the case, but little particles or little packets of energy called photons. And the energy of a photon is given by that same equation that Planck came up with, which is h times the frequency. Or it can be written as h times c over lambda. So again, just that relationship between nu and frequency gives us two forms of this equation that are both equivalent. And so in reality now we have a second equation for photons that relates the energy of a photon to the frequency. And so these photons are again, little packets of energy. You can almost think of it in analogy to matter. So matter is made up of atoms. You can't break down matter into any smaller piece than an atom. And similarly, if you have a beam of light or any form of electromagnetic radiation, you can't break that electromagnetic radiation into a smaller piece of energy or a smaller particle than what's called a photon. So this is kind of, there's that analogy between the two. And so then the way this explains the photoelectric effect is that if you have red light, each of those photons has too low of an energy to eject an electron. It doesn't matter how many photons you give it, one photon can only inject one electron. None of them have enough energy, and so it doesn't matter how many photons you add, you're not going to get a single electron off. Whereas when you go to higher frequencies or shorter wavelengths, the energy of the photon is now larger, and that results in you having now enough energy to kick an electron off the surface. Now the equation that Einstein came up with, which we're not going to really do any problems on, but I think it helps explain the concept a little bit better, is that you can measure the kinetic energy of the electron that comes off the surface. Again, that's 1/2 mv squared if you've taken physics before. But the energy of the electron as it moves off the surface is given by, again, 1/2 mv squared. It's mass times its velocity squared. And that's equal to the energy of the photon, h times nu. So this nu here is the photon frequency. Minus h times nu 0, as we'll abbreviate it, where this is what's called the threshold frequency. Alright, so if your photon frequency is below the threshold frequency, your photon does not have enough energy to kick an electron off the surface. If it's above the threshold frequency, some of that energy is going to be used to just release the electron from the surface, and the rest of that will then become the kinetic energy 1/2 mv squared. So this is kind of the concept behind photoelectric effect. As I said, we're not going to do numerical problems with this, but this I think helps drive home the concept. And so this was again another experiment that showed that light is not purely made up of electromagnetic waves and doesn't have this continuous property, but rather it's made up of little discrete packets of energy called photons. And then the last one that we'll go through that kind of illustrates this sort of paradigm, this relationship between electromagnetic radiation and matter, is the de Broglie wavelength. All right, so this, again, physics stuff, so we're not going to hold you responsible for these equations directly, but we just want you to know the concept. So Einstein has this equation that you're all familiar with. E is equal to mc squared, which kind of states that there's a relationship between energy and matter, that there really is no distinction between them. Energy and mass are related to each other. So the amount of energy that something has is its mass times the square of the speed of light. And if we're talking about photons now, so what de Broglie assumed was that, well, this equation applies to both light and matter. So if we have a photon, let's calculate the effective mass of a photon by just rearranging this equation. We're going to probably run out of room if I do this. Let me move this over a little bit. So this was Einstein's contribution. He already come up with this. And then what de Broglie did was say, well, let's just solve for the mass of a photon. If we have some energy for that photon divided by c squared. And we saw before that the energy of a photon in terms of wavelength or frequency is a pretty simple equation that we gave you on the last page, h times the frequency, or alternatively h times c over lambda. So we just replace that. And then when we solve, we get h over lambda times c. And then if we rearrange this equation then, so now we have a relationship between mass and wavelength, which is just crazy to think about because we think of those as being two separate things. Something either has mass or it has wavelength. It doesn't have both. But in reality, there's this duality between matter and electromagnetic radiation. There's no real separation between them. So if we then solve for wavelength using this equation, lambda is equal to h over mass times velocity. So again, for matter, we have some arbitrary velocity v, and we just solve for the wavelength, where v in this case is velocity. Now, it's kind of hard to demonstrate this in normal systems, and actually de Broglie was purely theoretical physicist. He didn't really do experiments on this. He just kind of came up with this idea. Legend has it that he has one of the world's shortest PhD theses. It was about 1.5 pages, where he just said, this is it. This is the de Broglie wavelength, and this is a new idea in physics, and people were just blown away by it, where it kind of suggested that, again, matter and electromagnetic radiation are not two separate entities. They're actually one and the same, and there's no distinction between them. Now, it's still, why was this not recognized before? The reason is that if we see this equation here, first of all, remember that h is an extremely tiny number, 6.666 times 10 to the minus 34. The mass of normal objects that we would study in our everyday life are, on the order of a few grams to hundreds of kilograms. So the point is, if you have a regular everyday object moving at a regular speed, because h is so small, the wavelength of that object is going to be minuscule. So, if I threw a baseball to the back of the room, back in my heyday, I could probably do about 70 miles an hour or so. And if I were to throw a baseball to the back of the room as fast as I could, the mass of a baseball is maybe like 500 grams or so. I'm not sure if that's right, probably less than that. But, it's on the order of a couple hundred grams. The velocity would, again, be about 70 miles per hour, which is roughly 140 meters per second, I think. The other way. It'd be 35 meters per second. Anyway, put those numbers in, calculate the wavelength of a baseball. It's going to be, something on the order of 10 to the minus 20th meters, which compared to the size of a baseball is not noticeable. So for regular everyday objects, their effective wavelength that you would calculate is extremely tiny compared to the size of the objects. You don't even notice that it's happening. But if you have an electron, let's say, which has a really small mass, and you put it in this equation, now all of a sudden you can start noticing that even things that we would classify as being matter, like an electron, have noticeable wave-like behavior. So really, all of these three experiments sort of demonstrated what's called the wave-particle duality, which is that matter and energy both have dual particulate and wave properties. All right, so they have both dual particulate and wave properties. There's no distinction between them, even though in many cases you don't notice the wave properties of matter because the matter is too big, or you don't notice the particle property of electromagnetic radiation, depending on what context you're studying it, but they are both existent. And then where this was kind of later demonstrated more directly, so as I said, de Broglie came up with this in a purely theoretical construct, but then there were some experiments further down the line that validated this, which is to look at the behavior of electrons in more detail. And it was found through a series of more sophisticated experiments that they couldn't do at that time, but did later on, that electrons do exhibit wave-like behavior. So you can't see this in regular everyday objects, but for something tiny like an electron, the wave-like behavior does become apparent. Okay? So one property that they observe for electrons is